in session 2 times ago, right? Which was basically what I said is lots of stuff when I did the dimensional analysis session. That a lot of stuff falls out from just knowing that something is a number. Right? And in some sense, a great deal of the theory behind this, but really the fundamentals of all of statistics, data, science, whatever you want to call it, is based on the answer to one simple question. Just what's a number? Okay. Why I say that is, I mean, we sort of take statistics for granted. Right? I mean, I'm guessing a lot of you, if not most of you, are here because you just want to know the techniques of how to manipulate numbers. But numbers by themselves don't mean anything unless you either understand what a number is or what a number is for. Okay? And these are very, very deep questions. To start with, let's take the question of, take a coin toss. Right? So you flip a coin and you say, or a die, and you say that it has probability, or it's essentially, it's a fair coin, so it's going to land up heads half the time and tails half the time. Or therefore you want to say that a fair die is something that will land up each one of those 6 numbers equally. But we have a problem here, which is that how do you, that's just an assumption, or rather, let's put it in a slightly different way. You just start with that. You might start by saying, oh, this is a fair coin, or this is a fair throw of dice. But really, a great deal of the thinking goes behind this is, what does it mean for a dice to be fair or a coin to be fair? Why I say that is, if you throw a coin 3 times, it comes heads twice and tails once. Well, do you know if it's fair or not? In fact, most of the time when you throw a coin, like if you look at the cricket coin toss, right, at the beginning of the match you have a coin toss. They don't throw it 17 times, they throw it exactly once. And the assumption somehow is that it's supposed to be fair. So really, what does it mean for something to be fair when you have seen it once? And that's a very, very hard question to answer. The typical answer to the question of what's a fair coin is, if you throw it many, many, many times, it broadly lands up heads and tails equally. That's the claim. Now, there are 2 problems here. One is that, of course, a real coin will rarely be exactly equal. There are imperfections in the coin, there's something that's going on. It's a physical entity, it's not symmetric. So obviously there is wind blowing, whatever it is, so you don't really know whether it's going to fall equally, of heads equally often and tails equally often. But there is no mathematical answer to that question, right? And that's how the assignment of probabilities makes sense. So the assignment of probabilities basically is that an event which has probability 1/2 should be one which in the long run, suppose that let's again call it heads and tails, that the number of times that heads shows up divided by the total number of throws, let's call that n, and the number of times that tails shows up, again let's call that, right, so divided by n, both should converge to half. That's why the probability makes sense. So for example, if you said that something was an event of probability 1/2, but in the long run, the number of, if you keep tossing it, it shows up 0.51 times. Then there's a problem, right? Because the probability 1/2 is generating an answer which is probability 0.51. And so clearly there's something wrong, because if that was the case, you can make money. Right? Because if something, people here who work in the finance business know, right, that something that is supposed to be random and chance actually happens 51% of the time, well, you have free money to be made right there. Right? So therefore, there has to be a match between the predicted outcome and the actual outcome. right? And the law of large numbers is a way to quantify that. Right, so a fair die has probability 1/6 of turning up any of the choices. That in the long run of many, many throws, each face will land up 1/6 times. Without the combination of the first and the second, probability doesn't make sense. Because there's no systematic way of assigning numbers if those numbers aren't consistent. Okay, so this is a very, so again, if you know that something is to be a probability, it has to match certain criteria, right? That there has to be a match between the number that you assign as a probability and the number of times that something happens in the real world. Okay, so you can run simulations of the number of times, 1, 2, 3, 4, 5, and 6 show up, and you can see that the mean value of many, many throws, here it is about 1,000 trials, is right in the middle. Right? So 1 plus 6 divided by 2 is 3.5, right? So the average that you would expect is what this thing converges to. Okay? So what this tells you is that at least the world of numbers behaves the way you want it to. The real world doesn't, because coins are never really, really perfect. But at least in the perfect world of numbers, there's a consistent way to assign probabilities to events. And just that alone, and knowing that something therefore has a certain kind of distribution, allows you to make very strong predictions. Right? So in the case of coins and dice, what is the underlying assumption? Which is that one throw doesn't depend on the next throw. Right? So if I throw a coin once, the next time I throw it, unless I'm a very, very good gambler, I can't really influence the next throw, right? So therefore, the definition of there being no influence is that the previous events don't affect the current event. Okay, and that's called independence, right? And independence is a very, very important assumption in older kinds of statistical accounts. Right? So the normal distribution, which all of you must have heard of, really arises from independent events. So let's take again, going back to the mortality rates. We know that smoking probably reduces your life, right? So clearly, you can't call those smoking and average lifespan as independent variables. But the claim is that if you look at mortality rates among smokers, so if you control for the variable of smoking, so you only test smokers, in fact you can even control for the number of cigarettes people smoke. So let's say that you take people who smoke 2 cigarettes a day, 5, 10, a whole pack, that if you take a large enough sample of smokers, you hope that their mortality rates are indicative of what their own bodies intrinsically are doing rather than the contribution of smoking, right? So this is the founding principle of statistics. Like if you actually want to do real world statistical analyses, you design your experiments in such a way that you pick variables that don't affect each other, right? So that's the way to conduct a study. So if you want to understand the effect of smoking on cancer, you make sure that your so you will have a control group, which is non-smokers, and then you have another group, which is smokers, and you want to make sure that the difference between the control group and the smoking group is only attributed to the smoking. So for example, suppose it turns out that group 1 had an overrepresentation of men, and group 2 had an overrepresentation of women. Now, women live longer, women may have lower incidence rates for cancer, they may also be less likely to smoke. So if that's the case, then you can't run a study of smoking's relationship to cancer on the basis of these two groups. Okay? So already, so what I'm saying is, when you are trying to design the study and asking what to measure, you have to make sure that the variables that you're measuring are independent variables. Otherwise, it's not that there is no other factor. So the law of small numbers is built into your study. Right? You are saying that the only thing that matters is cancer and smoking. You don't want the effect of age, you don't want the effect of gender, you don't want the effect of caste, and so on and so forth. Right? So the way to design a study, therefore, is to isolate out the effects of other variables. Now it may be in certain situations that it's impossible, that the variable that you have on your hands is impossible to separate out from other variables. And that's not that uncommon. In fact, let's take smoking itself. If you are saying that your smoking sample should be done in such a way that it averages over other possibilities, gender, caste, and so on, that itself may be a problem, because the way that smoking causes cancer in an adult man may be very different from the way smoking causes cancer in an adult woman. So you might think that by averaging out the gender variable, you have actually made the study more robust. But actually you might have made it worse, because what ideally you want to do is to look at the relationship between smoking and cancer for men and relationship between smoking and cancer for women. And you might want to dice that even further. You might want the relationship between smoking and cancer for men in their 30s, men in their 40s, and so on and so forth, because each one of those are non-linearly coupled variables. So the earlier kind of statistics, which assume that you could average over these dependencies, has its serious flaws. Okay? One of the places where we have discovered that the most is in voting. Why I say that is, the traditional idea of voting was, suppose that you have two, so in the Indian first past the post system, where you have exactly one winner in an election. Right? And the idea is that the person who gets the largest number of votes wins, everybody else gets zilch. Okay? Even if you got one vote more than the next person, you have all the spoils and the next person has nothing. Okay? Some other countries have proportional representation systems where you get seats on the basis of the percentage of votes your party got, rather than you as the first past the post person got. Okay? Why is the law of large numbers a problem there? So you might assume that in a well-designed electoral system, it's my ability to govern and my ability to produce good outcomes for the public at large that is competing with you. So I have some ideas. I feel like I should tax businesses and use that for social security. You might have exactly the opposite idea. You might feel like, no, I want to make it easier for businesses to thrive and reduce social security, because you're going to get that back in terms of better employment. These are competing ideas, and you and I as voters decide one is better than the other, and the claim is nothing else really matters. But actually, as we all know, in real politics, every single other variable that you think matters. Right? Caste matters, region matters, gender matters, age matters. So even though it's a system that was designed to average over other variables, in practice it is being used by people who are extremely careful about which seemingly incidental variables they want to optimize. Right? So in India, for example, you have tons of caste-based parties, even though caste is really not part of the Indian nation's, I mean, the electoral system was not designed to sustain caste parties, and yet it does. So you have, therefore, bad outcomes coming from institutional design that is faulty. Okay, so what I'm therefore trying to tell you is that law of large numbers is not some hypothetical thing. It has real effects on our everyday life. Okay? But to the extent that it works, it basically says that the average of a sample, right, of an infinite sequence of independent distributions, right, they with expected values ex1. So if all of them have the same expected values, then the unfortunately the math has gone out, but basically if you look at the average, which is the sum of the first n divided by n as n goes to infinity, converges to that number, whatever that common expectation is. Okay, so that's basically the law of large numbers. Basically it says in the long run, things behave the way you want them to. Okay. A great deal of course, what we are finding out is, even if the law of large numbers holds, the precise way in which things decay to the average is important. Why? Because in the real world, in the long run, we're all dead. That's the only thing that is true, right? So we all live in the short run. So the time scale at which things average out is far more important for us than the actual truth of the infinite long run. Right? So what I mean to say is, suppose you're going to take a coin which has half-half. If it's a fair coin, it goes to 1/2 in the long run. Okay? But if you know, and that is true if there are gusts of wind or other things that come up in the middle, right? Because those also average out. But if you know, and you're really, really smart, you know that for the next day there's going to be a lot of wind, and wind has certain predictable influences on the coin, you can use that to predict more coin tosses than chance. Right? So I can actually use, therefore, this is in economics known as the paradox is related to something called the efficient market hypothesis. Right? So the efficient market hypothesis basically says, in a perfect market, if there was money to be made by exploiting a difference, somebody would have done it, and so anyway it would have come down, so it would have regressed to the mean. But the fact of the matter is that in any finite market which is not perfect, there's always somebody who either knows more than what other people know, or who is smarter than other people, and so it's in that margin that you make a lot of money. Okay? So therefore, what's really interesting is the space between very small numbers and infinity is occupied by larger numbers where lots of interesting stuff is happening, right? And that's what happens in networks. Right? So this is just a comic illustration of that, right? So which is to say, if you think that the world will, right? So this is with enough samples, the probability of an event happening grows closer to a steady value, right? But that's true only if you make sure that all the assumptions are met. Okay? I mean, maybe somebody is flipping coins in such a way that, like, let's say that one of the sides of the coin is stickier than the others. I'm sure that will lead to a change. So you spill juice on your coin, that will change the way the coin tosses. All of these are information. Right? Ultimately, when you think about it, what coin tossing and randomness is telling you is, you have no information about the future from the present. But any such thing, whether it is the stickiness of the coin or it is the wind that's blowing, is information that you can use to predict better than chance how a coin is going to fall. Right? And that's really, that reduction of uncertainty is what everything is about. So for example, in a very, very big data world, you can imagine that you have futures markets that will be about Bangalore traffic. Right? So you can imagine, again, building a futures market for how fast you're going to get to work or wherever, right? And I will pay you money if you got there slower than that, and you pay me money if you got there faster than that. And so therefore I can build a futures market based on predicting. If I have very good predictive models for Bangalore traffic, I should be able to build a transportation system which actually optimizes that. Right? So I could tell you, so instead of my taxi service being based on distance, I could say it's free if it takes more time than X, and if it takes less time than whatever that x is, that estimated value, it costs this much. Those are things that one can build with sufficient data and sufficient modeling capacity. And network data is particularly problematic in that sense, or depending on how you think about it, has many more opportunities than you thought about. Right? So let's go back to the law of large numbers again and the mortality rates. Now it's clear the mortality rates are not independent events. So I inherit mortality rates from my family, so my genes make a difference. I inherit mortality rates from the kind of profession I'm in, the gender, all of those things. But broadly speaking, the claim is that your mortality rate should be predicted reasonably well by people who are close to you. Okay, so that closeness can be measured in geography. So people who live close to you are broadly in the same neighborhood, same income class, so on and so forth. Or maybe more abstract ideas of closeness like kinship or profession and things like that. Okay. So broadly speaking, if only things that are close to you matter, that can be averaged out. Okay, so you, instead of taking just you take a ball around you and you do the averages around the balls and you get something very similar to the large numbers. That's the way it works. So that's how, for example, in physics we are able to predict the temperature of a gas on the basis that only balls that are close to each other can interact. Balls that are far away from each other don't interact with each other. Okay?
Rajesh, see, this brings me to your hypothesis 1 and 2. That, this is how our mind works. And the other is that the worlds made that way. Actually, one of the things is that they both kind of influence each other.
Sure. But I'm saying that those two separately, and I didn't spell that out, have led to the two most important accounts of statistics. So
the two most important
accounts of statistics, right? So the frequentist account is based on the world working that way. So the idea is that you toss coins many times, and each time you get a heads, you put it in the heads counter, and tails, you get the tails counter. And when you average those two out, you get 1/2, right? But there is also a Bayesian approach to statistics, which basically says it's my belief. So I believe that it's a fair coin, and so I start with the assumption that the probability is 1/2, and each time I throw a coin, I update my belief about the coin to reflect all my first original belief and the trials that have taken place so far.
So my question from this, which is that are both these averages that I come out with from both these approaches, are they actually fuzzy averages?
No. I mean, in the mathematical version, they are precise. The phenomena they're modeling is fuzzy, but the maths is perfectly precise. Okay. The problem arises in networks because, as you can see, you can get connections that are pretty far away, right? Meaning, if my mortality, so you may do actuarial statistics based on the mortality of people around me, of my class and caste and so on, but you can't predict for an asteroid landing on your head, right? And that's the problem, which is that if there are systematic sources of influence that are from far away, you can't take those into account in the law of large numbers model, right? Because those are, it's not only that they are not independent events, because as I said earlier, if things were dependent but dependent in a localizable manner, that's still okay. But things that are dependent but in a non-local manner, or things far away affect you, then you have a problem, right? And that many of the complex issues that we face come from the poor understanding that we have of these kinds of network effects. So if you take the financial crisis, for example, it's precisely because, and I read this very interesting thing, right, that Ireland's meltdown was basically based on Irish borrowing money from abroad to buy homes from other Irish people, right? So you have this loop where you think that there is an inexhaustible supply somewhere else, but of course that runs into the ground somewhere. At some point, your creditor is going to say, right? So that's why small economies have a huge problem. The US can say, I'm not going to return your money back, what are you going to do? Right? But Ireland can't say that. And actually China and the US have a particular problem, because if China says, give me your money back, and the US says, yes, sure, then the US doesn't have any money to pay for China's products. If China, on the other hand, keeps loaning them money and they know they can't get it back, then it's a sort of dead investment, right? So this is a dynamic, and which is why currency rate manipulations, all of those are so central to this particular relationship, because you want to manipulate demand while knowing fully well that the only way that both the supplier and the customer are both locked into each other, and that's an issue. And the Chinese therefore are trying to develop internal markets. The US so far doesn't seem to have done much to do anything about its manufacturing base, but you never know, right? But that kind of long distance effect and what that does, I mean, there is a very pithy version of it, which is the butterfly effect, right? So you have a butterfly flapping its wings in the Amazon, and it leads to rain showers in Bangalore. That's a completely chaotic interaction, meaning nobody can predict it. But what's really interesting about network effects is that there are systematic, predictable, long-term interactions. Meaning, you know that if you keep borrowing money from across the world, and so that is to say that your energy and, in this case, money supplies from somewhere else, but all the spending and the consumption is happening here, that is invariably going to lead to problems, because on a day-to-day basis, you're only buying and selling stuff from the neighborhood supermarket at most. But actually Walmart is sourcing it from halfway across the world, right? So, yeah.
When such a surprise stuff happens, it's only a kind of a limited impact. It's in the long term it will still neutralize, right?
That's the claim of averaging again, which is that so one possible claim is that it doesn't come down like this in a very smooth way. It comes down like this, but still there's a overall trend to average out, right? So that's the claim made for bubbles in general. So the claim that so one of the most interesting studies done, and real estate bubbles are a good way to look at it, was on housing prices in Amsterdam. So if you look at how people have done, because Amsterdam keeps very good records, if you look at the housing market in Amsterdam, you can study it for the last 200 or so years, every transaction can be, right? So it's very good data that way. And what you find out is real estate is a good investment. Meaning, in the long run, gold and real estate and the stock market will beat the mean. That's the claim. But that's assuming that you don't have catastrophic meltdown. So the asteroid falling on the Earth, there's no getting away from that. So one therefore question is, what stage does the interaction become so powerful that there is a possibility of something which is catastrophic, right? Which, in the famous words of Donald Rumsfeld, right? The unknown unknown. The known unknown we can handle, but the unknown unknown is the hard problem. And in network situations, at least simulations, so obviously we haven't, at least in the economy, we haven't had that happen yet. The Great Depression and the more recent one that got over, and this one seems to be on its way out. But whether something will happen in the future that will be catastrophic before it stops, we don't know. Certainly for pandemics, people seem to think that sooner or later there will be either influenza or something like that that will wipe out lots and lots of people. Right? The other question is, what's your definition of acceptable damage? Right? The people who are involved in it certainly don't think that it was acceptable. So these are the issues. Why I say that is from a data science perspective. Like, how do you insure for these things? Right? How do you insure? And people are asking these questions. How do you insure for one-time events? Like, suppose you wanted a futures market for a nuclear war between India and Pakistan. How would you? What would be the basis for that kind of market? I don't know. But it's only in this era of networks that we can even begin to ask that question, right? Because it's a one-time event. I don't think we'll have repeated nuclear wars between India and Pakistan. Right? Similarly, there will be other such things. At the individual level, we know how to solve it. I mean, what's interesting is that the last 200 years has made individual insurance a solvable problem. Right? I mean, I don't know when, as far as I'm concerned, I'm going to die only once. Right? And so, but we now know how to buy insurance for one person. Life insurance is based on you dying only once, but there being some predictable pattern across people. But I don't know if we can aggregate all kinds, so you can have a market where you amortize nuclear war between India and Pakistan with economic meltdown because of revolution in China. I don't know how to even think about that, but that's the kind of non-linear aggregation that we're going to be looking at. Right? So networks can have these long distance effects, but the law of small numbers still holds, meaning you still think that you can predict or at least give some answer to the question what's going to happen in a very complex network based on some summary statistics of that network. And that's the great challenge. Right? So I think that the great challenge of data science in general is not, data science would be useless if Facebook or stock exchange data was a lot like old style insurance data. Because there you already know that normal distributions work. So why would you want, to show that 1 billion data points work with the normal distribution in the same way that 1 million ones do is not that interesting. But what's interesting about big data is that because of big data and the size of the big data, lots and lots of small statistics become far more interesting. Meaning, Facebook is not selling you advertising based on aggregate categories, right? It's not just saying, Rajesh is Indian, male, and married, and then use that to give me some advertising. No, they are doing very, very deep sort of analysis of the particular data that I'm generating to give you advertising. So that idea of how do you essentially look at the various deviations from the mean, which the normal distribution would have or other distributions, and how do you collect patterns of those deviations and deviations of deviations and so on is where a lot of the action is. Right? And it's, for example, therefore, you would have to, and I'm sure Facebook spends money trying to figure this out, which is that if I have 600 friends, but 400 are men and 200 are women, and of those 400 men, 200 are in India and 200 outside India. How do each one of those things actually give rise to different probabilities of being attracted to some product? So for example, suppose that you want to sell me an iPhone, what's the correlation between the number of global friends I have, so non-national friends, to your probability of buying an iPhone? That's something that I'm sure Facebook is interested in, or whatever other thing. Right? So there are any number of products where you can now, because you can get large enough numbers for each one of those. If you go back to what Anand was saying, the t-test is reasonably good with about 30 or so numbers, right? So what's happening is that with very, very large data sets, you can slice it and dice it in such a way that you can form lots and lots of different collections of 30 people. And the one that is the most predictive is the one that you should be using.
Ravish, correct me if I'm wrong, but there seems to be a dance between large numbers and small numbers.
Yes.
So I choose and I decide at that point of time to see where I can use what.
I'm saying that small numbers is where all the action is, meaning whether we are stupid or whether the world is made that way. By reducing a large set to a small set, you have the capacity to predict and generalize, right? So therefore the game is to transform some set of large numbers into a set of small numbers that you can do something with.
Localized connections,
Whatever you want. So that's not going to happen in a network. Local connections are great because then you know that it obeys something like a normal distribution. But it won't always work. Okay, so let's go back to the Fortune 500, right? And look at the play of the large and the small numbers. If you look at the top industries by profit, I don't know if you can see the third column on the right. You have network and communication equipment, internet services and retailing, pharmaceuticals, medical products and equipment, finally railroads, then financial data services. So you can see that the top 6 are all, except for railroads, you could argue that the other 5 of the top 6 are very modern inventions, meaning that most of these industries did not exist 100 years ago. Okay. Network and communication equipment definitely did not. Neither did internet services did not. Pharmaceuticals probably were not that large 100 or so years ago. So what this is saying is that somehow the largest industries that we have right now were non-existent 100 years ago. In the same way that dinosaurs ruled the earth and now they don't exist. So how do you understand this interplay therefore between, so how do you identify a winner? Right? Because that's where, if you are trying to make money, or how do you identify a threat which seems inconsequential now but might be particularly relevant in the future. I mean, that's where a lot of the thinking here is going, right? I read this very interesting piece by Paul Graham, right? How many of you know of Paul Graham? He runs something called Y Combinator. Okay, so Paul Graham has a very interesting idea of what a VC's investment policy. Even if you're a VC, the VC has a major problem on their hands. I mean, they're facing a bunch of crazy ideas. So one, if you go to a VC and I say, I want to open a top-notch French restaurant in Bangalore. I mean, that's not what you would go to the VC for, because you kind of know what doing a top-notch French restaurant is about. I mean, so therefore the risk, there's a risk there, but it's a known risk. And so there is, your returns therefore are also not going to be unexpectedly large. Right? I mean, if it fails, it will sink whatever money you have spent in it, but you can sort of insure against that failure. So a VC therefore is in a business where you want to invest in certain things that succeed well beyond expectations. Right? So which is to say that if you put in $1 million into 100 companies and 99 of them fail, but the 100th one makes $101 million, you have a return on your investment. Right? So that's that kind of thing. So how does one identify the winner in a situation where almost everything is going to fail? And that's really the challenge of this kind of big data science. I mean, there's one system that has sort of worked that out. Right? Evolution has figured out of all the possible species that could have existed on Earth, only a tiny fraction are still alive now. And many more are disappearing, but the fact is that predicting which species will survive in the future and which won't is, we don't even know how to answer that kind of question, but nature is able to figure that out. So, how do we understand that kind of nonlinear increase? So whether it is nonlinear increase in income of a startup, or catastrophic failure for economies as a whole, or climate change and what it will do for the Arctic ice. All of these are questions where we want to predict the long-term impact of extremely small shifts, which nevertheless have to be predicted. So if we can do that, then we have a real data science. So I'll stop with that today, and we need to have a little discussion about the projects.